All right, so we're gonna go into how to create an electronic speed controller or ESC for controlling brushless DC motors like this one. Before we get into that, I want to say that this project is not for beginners. So if you are still playing with Arduino or Raspberry Pi, this is probably not for you. You have to be comfortable with writing C code and be able to know how to play with processors at the register level. And the reason I'm saying this is not for beginners is because we're dealing with hundreds of amps coming out of batteries that will really quickly burn your system and possibly ruin your computer if you're not careful. So if you want to throw money away and you're a beginner, then by all means go into this project, but know that you're probably going to burn stuff. You may create a fire in your house. So I don't think you want to get into that. So having said that, this is a project that will be comparable to what you find uh, at a commercial level. This will be able or should be able, given the processor we're going to be using, and we're going to squeeze every clock cycle out of it, we're going to be able to run motors upwards of 700,000 electronic RPMs. Okay, so it will be really fast, should be able to handle 40 amps, at least with the MOSFETs we're going to be using. And once we write the code for this one, we're going to transfer it into the equivalent PCB version of it. I will have the links in the description on where to buy all the components and the breakout boards, so you can do your own thing. But let's go through the layout, see how they're connected, do a high-level review of the entire process. In this video, we're also going to implement or write some code to implement the communications between the flight controller and the processor to be able to control the motor itself. Right? You don't want to hard code speed test runs into the processor and burn your stuff, not be able to stop it. Okay, so let me show you the layout. So let's go through the components first, and then we'll go through the connections. Processor, we're using ST's entry-level ARM processor that can run at 64 megahertz. Part number is G070 KBT6. The driver for the MOSFETs will be this with a, I don't remember the name of it, it's an ADP driver, 1 microfarad, high voltage, 100 volts is recommended. High voltage diode as well for bootstrapping. The capacitor is for bootstrapping as well. Source bypass capacitor of twice the value of the bootstrap capacitor, so 2.2 microfarads, 25 volts. The comparator needs a 0.1 microfarad filtering capacitor, high voltage as well. The breakout board has 3 resistors for creating the floating ground. So this will be connected to the back EMF signals of each of the phases, which in turn will join those signals to create a floating ground to compare the back EMF signal against it. Okay, and it will give us a signal whenever the signal crosses either up or down the floating ground. 2 regulators, 3.3 volts for the processor, 10 volts for the drivers, the MOSFET drivers. 6 MOSFETs, 2 for each of the phases, high and low. And you can see the connections here. And then 6 4.7 microfarad high voltage capacitors, 2 for each of the phases. And obviously we have the connection here for each of the phases of the motor. This will be the driving line. It's also the back EMF detection. And it also connects to the SW pin of the driver for bootstrapping purposes or being able to drive the MOSFETs. So if we follow A, it goes and connects to the low side drain pin of the MOSFET. It also connects to the source of the high side MOSFET. it goes back to the SW pin of the driver, and it comes back to the comparator for back EMF detection. So we have 3 lines coming back in, and again, they're joined here via the 10K resistors to create a floating ground, and that floating ground is used to compare against the actual back EMF signal, and then the whenever something happens or the signal changes, then the signal on this line changes as well, and we use that for zero crossing detection over here. Okay, 1000 microfarad 50 volt capacitor. The power rails, we have 1, 2, 3 24 power rails. We have 2 grounds, normal grounds, and then we have a separate ground that is connected via a 2 ohm ground resistor or 2 ohm resistor, just to create high impedance for the noise, to keep the noise down here instead of going all over the PCB board. So we want to keep this place as clean as possible. So that's why I'm calling it a 2 ohm ground, right? And then we have a 10 volt rail that goes again back to this. By the way, the comparator is connected directly to the power rail, 24 volts. And then we have the 3 volt, 3 volt rails. This one is the one coming from here. It powers the processor. We have also one to the header of the programmer, the ST-Link V2, to power this if it's not connected to power. The processor, we're using the SWC or the clock and data lines pulled up via 1K to 3.3 volts, and it goes back to the header of the ST-Link programmer, clock data ground and 3 volts. We have 3 lines, 3 output lines, outputting a PWM signal for driving the Mosfet drivers, and 3 output lines for enabling and disabling the drivers themselves. And then we have 3 lines for interrupt detection of zero crossing. So we have A, B, and C, right? And then we have the output lines A, B, and C, and the PW lines A, B, and C. So that's about it. So I will include a link for this layout so you guys can study it and do your own. And now we're gonna go and implement ProShot and detect the line. So here's the program that we're gonna use to send the signal to the flight controller, and then the flight controller will send it to our processor. So let's look at the signal, see what it looks like. So that's the signal at 0, right? We have 4 bars. So this 4 bars, or the first 3 bars, is the signal we want. So 1, 2, and 3. And this is CRC. We don't care about a signal. We're only going to process the first 2. And right now, the bar or the signal is at 0. So the bars, the width of those bars or that signal is 64 clock cycles or 1 microsecond. The 64 clock cycles because the processor will be running at 64 megahertz. And every time each bar increments, or at least the first 2, it increments by 8 clock cycles. So we know the base or 0 would be at 64, and every 8 clock cycles represents a 1 on those bars. So let's go write some code and implement that protocol and see what it takes. Shouldn't be that difficult. Oh, actually, let me just show you as we move it what the signal does, right? So that's what we want to capture. All right, so let's go create a project. I'm using STM32G0 IDE. You can download it free from st.com. And the code we're going to write should work with any of their processors, provided they have the timers and they can support DMA, or you just want to do it via PWM. Part number is the G070KB. Okay, we'll get this. Click Next. C++ project The name will be ESC breadboard. Click finished. Almost done. Okay, so here we have it. First thing is to set the clock rate, 64 megahertz. Press enter. This pop-up comes up. Click OK. It's going to configure everything for you. You can see this one just switched. So it's trying to find the proper configuration to configure everything at 64 megahertz. It takes a few seconds. Almost done. Okay, it's complete. So now we'll go and tell it that we're going to be using serial communication to program it. And we are going to implement the protocol. And if we go here, again, it says ProShot on this one, but we're actually going to do it on pin 30 right here. So let's go back to this. Click on this one, and it says it's connected to timer 1, channel 3. So let's use that. Let's label it for future reference. And we'll go to timer 1, channel 3, input capture. So we want to capture the falling and rising edge. So we'll do both edges. We'll implement DMA. So it's done by hardware instead of software. And make sure it's on channel 1. This one needs to have the highest priority. And the reason for that is when you're testing, you want to make sure you want to be able to power off your motor when things are not going right? You don't want to let it get stuck at high speed and now you don't have a way to power it other than removing the power. If you remove the power when it's flying really high, you're going to create a giant spike that is going to fry your system, right? So you don't want to do that. And the interrupt has to be enabled. It's already checked. So we'll generate the code. Okay, and we said it was C++ project, so we'll create a source folder, name it CPP, and another folder for our source code or files, and then a source file named CPP, header for the main file, and then to declare external variables from the C source. The loop, and let's add this declaration in the header file. And call it before the loop. This will transfer control back to our file here. So first thing we need, obviously, we need access to the timer. And it's already being declared here. So let's just add it to this one so we have access. Create a setup function and call this function from main. Okay. So now we need to launch the DMA or the input capture using DMA. And to do that, we just call this function, input capture, start DMA, use channel 1, timer 1, and we said it was going to be on channel 3. The data, we don't have this variable, but we're going to create it. So it will be DMA signal. The length will be 16. The reason it needs to be 16, I don't know if I mentioned it at the beginning, but let me bring this up again. So we are going to capture the rising and falling edge. So it's total of 4 bars. We need 8 signals. But because this signal is always coming, we may end up launching the DMA in the middle of it. So we would capture an incomplete signal, or at least not in the right order. So we may capture this at the beginning, and then this one's on the back end. So we'll capture twice the amount, 16 in this case. So this signal will have a valid signal somewhere in between those 16 values. We just need to get that out of those 16 values. Okay. So this has to be cast to a 32-bit, and it needs to be clear. So this will be an 16-bit. Let me check this, make sure that this was done correctly. So the DMA, this one has, okay, it needs to be set, leave at normal, and the data width has to be 16-bit. So there we have it. Everything's correct. And this will be an array, 16. So this will capture the data, but this is going to trigger a DMA, so we have to capture that trigger as well, or the interrupt, not trigger, but the interrupt. So let's write that function, capture callback. And this one takes a timer handle. So let's check for the right timer. Make sure what is triggering this function or is interrupting this function is the timer we need, which is the timer 1. And also let's validate the channel. So it needs to be channel 3. This one more. Timer active channel 3. And if we have this, that means that it is the right timer and the right channel. So we can set up a flag to tell us, hey, your data is ready, go process it. So new DMA signal equals 1. And let's declare this. Let's set it to 0 from the beginning. So now this will capture data. We want to capture data in a continuous loop. You can see I didn't finish this line. There it is. So inside this loop, we'll say if a new DMA signal, then we should go and process DMA signal. We don't have that function yet. We're going to create it. And then we launch it again, right? So we'll copy this. And something might be wrong there. Anyways, so we'll create this function here. And new DMA signal will set to 0 here. It's the first thing we want to do. Right, so whenever we capture data, we can go here. Let's compile this code, make sure it works. No errors. Let's launch the debugger and see that if we can capture the data now and see what it looks like. All right, let's launch it. So it's in this function, which means that we capture the signal because a black flag was set, and this was called, and then it's going to be launched again. So the data, we should have data here, and we do. You can see we have all those values. So let's move it into the live expressions and let this one run and see what the data looks like as it's being captured. So there's the data, right? It's all over the place. It doesn't make any sense. Well, it doesn't make any sense because this is just clock cycles, the difference from one to the next. So we need to normalize the data to the point where it starts to make sense. So to normalize the data, we'll need another array. And let's let's call this normalized, and let's do a loop here. 15, and we'll say we'll store the values of whatever DMA signal index plus 1 minus the current index, so DMA signal whatever the current index is, right? So this will give us a better view of what we're getting. I'm launching the debugger again. I just pressed the F11, and we'll look at the normalized data and see what we get. All right, so let me bring this over to live expressions. And this is the raw data all over the place. Let's look at our normalized data. And this one's more stable. It actually looks pretty good. We said that the signal at 0 is 64 clock cycles. There it is. Even though it moves to 65, possibly 63, it may go 66, who knows? So we need to normalize it some more, and we need to stabilize the data so it stays solid at 64, or whatever number we decide is a normalized number, right? So let's create a function that will round up and down depending on the number we're using to divide. So we'll create one more function, and let's call this closest. It takes two values, a and b, and this is a simple one. I got this from the headers of C++ libraries, so you can go and look at it. It's pretty simple, or you can write on a piece of paper and you'll see why it works, right? We're doing unsigned integers, so it works perfectly for this. And we're going to return a plus b divided by 2 and divided by b. And this will give us a better number. Now also, because the base number is 64, if you divide that by 8, it will give you 8, right? And the increments are 8 clock cycles as well. So we can divide this signal by 8 and then remove 8, and we'll end up at 0 when it's 64. And then we'll have 1 when it's 8, and 2 when it's 16, and so on. So we'll use the closest. So we'll divide it by 8 minus 8. And let's press F11 again, launch it one more. And this will give us something usable, a stable signal that doesn't jitter or dither all over the place. Let's go to live expressions. So there's our raw data. This is our normalized data. This is something we can use, right? It's perfect. It doesn't move. The only thing moving is this big number. But that number is representative of the gap between one signal and the next signal. So we're going to use this big number to determine where a good valid signal starts. And we only care about the first 3 bars, which means that if this is the third bar, then this would be a gap. This would be the second bar. This would be a gap. This will be the first bar, and this will be a big number. So we can detect up to 10, right? So we can iterate through this list of elements up to 10. And if we find a big number anywhere in between from 0 and 10, then the next values have a valid signal. If we find it at 11, we don't have enough values to get a valid signal. Okay. And now that we have this, let's look at the signal. And let's see what it looks like when you change it. Right. So there is our signal there. And so Beta Flight is behind it. Let me move it to the bottom, move this to the top. Right there. So if I move the slider to all the way to the top, you can see how the bars went all the way to the right. And then we have these numbers here that change. So this is representative of a bar, another bar, and this is the number, the gap between the two. So when Beta Flight is at 0, or when the signal is at 0, you can see the gap increases, the number increases as well. So the 0 is the actual bar. right? And you can see it doesn't move. It also tells us that the maximum value is 15, right? So we go here, it's 15, 15, and 14. Now these are valid, so it's 15 times 15 times 4, and that will give you 1023. That's the actual signal, 10 bits. That's a full throttle, is 1023. The reason this one's 14 is because this is not shouldn't be divided by 8, because that signal only goes 1, 2, 1, 2, 3, and it goes back to 0 because then this one increments. And then once this one gets to 15, it goes back to 0 and this one increments. Okay, so now we can go and do the final coding to detect or look for this number and then get the right signal and then do the calculations to get the actual number, right? So let's do that. So first, let's look for that big number. And we say we could only go as high as 10. And so we're gonna look for DMA normalize index. If this one is less than, let's say 100, right? Because the biggest number we can get is 16 anywhere in here. So if we get anything below 100, we can assume that is a valid value, but we still don't have the beginning of it. So we don't know where we're at. So the value becomes invalid until we come across something big. So if it's not big, we'll just dismiss it, continue to the next value. If it falls through, that means we're good and we break out of it. So here, now that we have a valid value, let's create one more variable so we can store this value. We'll call this motor speed, set it to 0. So now we can say motor speed equals the DMA normalized index. Now remember, we are here, right? So we want the next one. Let me change this so the signal looks familiar. It'll be 0. So we are here, we want the next one, and index is currently pointing to 7. So we are going to say index plus 1, and because it's 3 values, and I know this one represents the most significant 4 bits, I'm going to move it, and it's a 10-bit signal where I'm going to move it 6 to the left. And I'm going to do the same for the other ones. I'm just going to move them different values, different ways, so we can capture the data. I know what I need to do, so I'm just going to go and increase this one to 3 because we just got this one, and we need. So we are the index is here. Plus 1, we get the first bar. 2, 3, we get the second bar. 4, 5, we get the third one. So this is plus 3. This one has to be shifted twice or 2 bits. And this one is plus 5, and it needs to be shifted 2, but this one's to the right. And that will give us the actual value of the signal. So let's press F11. And press F8. Go to live expressions. We have the raw data, normalized data. So let's collapse this. We don't care about that one. Have that data. That's valid data. So let's bring in this new one. And you can see we have 0. But if we bring this over and we go all the way to the top, now we have 1023, which is the maximum value, 10 bits, right? So our processor or the PWM signal we're going to be working with is going to be running at 64 kilohertz on a 6400. I mean, at 62 kilohertz on a 64 megahertz processor. So it will be running at 10 bits, right? So this is perfect. It's a one-to-one match. And, obviously we go to the bottom and we go up 1. It gives us 24. The reason for that is because this is designed for going from 1,000 to 2,000. So there's a 2,000 here. I'm guessing because at the beginning it was only PWM signal going across, and now there's new protocols or different protocols. So it needs to start at 1 plus 23, right? And then if we increment by 100, you can see the signal here keeps going up and up until it reaches maximum. Go back to 0, go back to 100,000, 100%, and 0. And if we look at the signal here, so we can see what it looks like, you'll see the number here change as well, along with the signal itself. So there's 100%, right? 0%. We do 10% increments, and it works. So that is it for this video. On the next video, we will do a full configuration, and we're gonna try to write the entire code for running the movers. Hopefully, we'll get to optimization as well. The total count of lines, I'm anticipating there's gonna be around 500 lines of code. So we'll see if we can type all of that in an hour. That's a lot of code to type, but we'll see if we can do that and get it to work on that same video. Hopefully, it won't have to be 2 additional videos, but 1 more. All right, so that's all I have to show for. This is a must for the next step. So if you want to do this, you have to implement ProShot or some type of signal to be able to control the motor at any point of your testing phase. So until next time, enjoy.